Okay, so thank you everyone for coming to this fourth seminar of the PRIMO group. Today I have the pleasure of introducing Patricia Diaz de Alba, which is an excellent postdoc at the Gran Sasso Science Institute. She got her PhD at the University of Cagliari, where she then held a 2 years postdoc position. And she's been working on several stuff, among which inverse problems in geophysics, quadrature formulas, and integral equations. Today, she will give us a talk about 2D reconstruction of subsoil by EM data inversion, so on the inverse problems of geophysics. So please, thank you.
Hello to everyone. Thank you, Alessandro, for the introduction. As he just said, I am very new at the GSSI in L'Aquila. I'm a very new postdoctoral researcher here, and today I will talk about two-dimensional reconstruction of the subsoil by electromagnetic data inversion. So the motivation or the aim of this research line is to reconstruct the electrical conductivity of the soil by electromagnetic induction techniques. This kind of techniques has been used since the late 70s in order to characterize the spatial variability of soil properties of the subsoil. These EMI sensors have been developed in response to users' needs and also in response to the available technologies, improving the functionality of these tools. It has been a lot of benefits. For example, the large amount of georeferenced data that can be collected rapidly and inexpensively, and in order to get a more complete reconstruction of the distribution of the electrical conductivity than on other techniques, but however, it also has some limitations. For example, the results are site-specific and can be varied depending on the interaction of the different soil properties. But despite this, it's been increasingly used, and it allows to get very good results. So it was initially used to assess soil salinity, and nowadays its use has expanded also in many other applications like hydrological and hydrogeological characterizations, agriculture applications, archaeological surveys, and so on. So the main device used in applied geophysics in order to collect the data that we need to invert is the ground conductivity meter. Basically, it has this device has two coils, a transmitter and a receiver. The transmitter sends electromagnetic waves into the subsoil, generating an electromagnetic field, which is called primary field, and in the picture is represented by the green line. This primary field sends small eddy currents, generating in turn a secondary field, which is represented by the blue line. And this secondary field is sensed by the receiver. Then the ratio between the two magnetic fields is recorded by the device as the apparent conductivity of the soil. And this apparent conductivity is the data that we need to invert in order to go back and reconstruct the distribution of the electrical conductivity of the subsoil. So now that we know how to collect the data that we need to invert, in order to solve the mathematical model that describes the interaction between the device and the subsoil, we need to also discretize in some way the subsoil. So the discretization that, there are, during the measurements with the device, there are some parameters that can be varied in order to get more data and in order to reconstruct in a better way the distribution of the conductivity. And these parameters are the orientation of the device, because it can be used in vertical and horizontal orientation, the height at which the measurements are taken, the angular frequency of the device, and the distance between the transmitter and the receiver, so the intercoil distance. As I was saying before, we need to discretize the subsoil in some way in order to solve our mathematical model that I will show you in a few seconds. And the discretization that we use is the following one. So we assume that the soil has a layered structure with 10 layers. The K here represents the thickness of the kth layer. We assume that every layer has the same thickness. Sigma K and mu K are the electrical conductivity and the magnetic permeability of the kth layer. Rho is the intercoil distance. H are the heights at which the measurements are taken. And Z is the depth in meters. So now that we know how to collect the data and we know the discretization of the subsoil, we can be able to solve the mathematical model which describes the interaction between the device and the subsoil in order to reconstruct the electrical conductivity. So there are two main models. The first one is a nonlinear model, which is composed by two freedom integral equations of the second kind, and was introduced by Wade in 1982. And the second one is a linear model, which is also composed by two integral equations, and it was introduced by McNeil in 1980. So it is obvious that the main difference between these two models from the mathematical point of view is the nonlinearity of the first model with respect to the second one, and this is okay. On the other hand, there is a very important difference between these two models from the geophysical point of view, and the difference is that the linear model, which was the first introduced model, it is accurate just in the situations in which sigma, which is the electrical conductivity, takes small values. When I say small values, I mean like 100 millisiemens per meter, which is very, very low. So it was first introduced for a specific device, which works with 1 meter as the intercoil distance, and if I remember well, 14,600 hertz as the frequency. And it was introduced for low values of the conductivity, which means that if we want to study an area and we know or we suspect that the electrical conductivity can take high values because maybe there are conductive substance in the subsoil, we cannot trust in the linear model anymore. So that's why 2 years later, the nonlinear model was introduced by Wade, because this model is accurate in every situation. So when the electrical conductivity is high and also when it's low. And this is why I want to focus today on the resolution of the nonlinear model. So this is the nonlinear model, as you just saw. It derives from Maxwell equations, and it can be written in this way here, where the first equation corresponds to the vertical orientation of the device. That's why there's a V here. And the second one corresponds to the horizontal orientation of the device. Rho is the intercoil distance, so the distance between the transmitter and the receiver. Lambda is the variable of integration and represents the ratio between the depth and the intercoil distance. J0 and J1 are Bessel functions of the first kind of order 0 and 1 respectively for both the orientations. MV and MH are the measured data, so the apparent conductivity of the subsoil is the data that we need to invert in order to reconstruct the distribution of sigma, and R is the reflection factor. So I want to remark here first that the measured data, so MV and MH, are complex valued functions. So the apparent conductivity of the subsoil is complex. The real part of the data is called the in-phase component of the signal. And the imaginary part of the data is called the apparent conductivity of the sigma. So I wanted to tell you this because from now on I will talk about in-phase and quadrature components, so you will understand what I mean. So the data that we invert is complex data. And now the interesting thing is that our unknown in this mathematical model is inside this reflection factor function, which is defined in this way here, where N0 is calculated by this formula here, which represents the characteristic admittance of the cave layer. And at the numerator of Nk, we have this factor in which we find our unknown sigma, which is the electrical conductivity that we need to reconstruct. Y1 is calculated by this recursion formula, which denotes the surface admittance of the cave layer. So from now on, we will assume that we know the distribution of the magnetic permeability mu, and we will reconstruct sigma. There are some works, some papers in which this mathematical model has been solved. In the first one, which was written by Giampiero Deita, Caterina Feno, and Giuseppe Rodriguez from the University of Cagliari, they inverted multi-height data, so data recorded at different heights above the ground, and data which was collected by a device which works with one intercoil distance and one frequency. They inverted just the imaginary part of the data, so the quadrature component of the signal, because in general, the electrical conductivity of the soil can be considered just the quadrature component of the signal. So they inverted just the quadrature component of the signal, and they got very good results. In this work here, which was written by myself and by Giuseppe Rodriguez from the University of Cagliari, we inverted multi-frequency data, so data recorded by a multi-frequency device. And we also studied the in-phase component of the signal, so the real part of the data for the first time in literature. And we obtained very good results in the sense that it is true that that if you want to reconstruct the distribution of the electrical conductivity, you can invert just the imaginary part of the signal, but it's also true that if you neglect and ignore a part of the data, so the real part of the data, you are losing information anyway. So there are some situations in which if you study also the in-phase component of the signal, you are able to reconstruct the electrical conductivity in a better way, a more complete reconstruction. Then we wrote also, we applied the same mathematical algorithm to reconstruct the magnetic permeability of the subsoil. So we assumed that the electrical conductivity was known, and we reconstructed the magnetic permeability, which wasn't done before in literature. And we also got obtained very, very good results. So what we do in this work is to reconstruct the electrical conductivity sigma by inverting multi-coil data. So data recorded with a device which works with different intercoil distances. We verify the effectiveness of our numerical algorithm on synthetic and experimental data. We invert for the first time the complex signal entirely, because till now the real and imaginary part were inverted separately. So we inverted the in-phase component of the signal, and we inverted the quadrature component of the signal, but not the complex signal in its entirely. So this is done in these two works here for the first time. We introduce non-smooth regularization. I will explain you in a few seconds why we need a regularization. And we also introduced the concept of the depth of investigation. So now I will show you which is our numerical algorithm. We set first the vector rho, which contains the different intercoil distances of the device, omega, which is the vector which contains the different frequencies of the device, and h is the vector which contains the different heights at which the measurements are taken. And we consider the data B for both the orientations of the device. So what we want in this work here is to reconstruct the conductivity sigma, which approximates in the best way the exact data and the recorded data. So basically, we want to approximate M, which is the measure, the exact data, approximate the exact data to the recorded data B. So we vectorize in lexicographical order B and M, and the best approximation sigma star that we are looking for can be obtained by solving this nonlinear least squares problem. So we minimize the norm of the residual function R, where the residual function is defined as the difference between the measured data and the exact data. And this residual function takes complex values, as I was saying before. So in order to solve this nonlinear least squares problem, we apply the Gauss-Newton method, which is an iterative method. So we first linearize the residual function in this way here. So the residual function in the step k plus 1 is approximated by the residual function in the step k plus the matrix Jk, which represent the Jacobian matrix of the residual function with respect to sigma in this case, because we want to reconstruct the electrical conductivity sigma, times this qk, which is a step length, and I will show you how to find it. So here I want to remark that we work with the analytical Jacobian matrix. So we computed the analytical Jacobian, and we saw that the computation time of the analytical Jacobian matrix is much smaller than the computation time of its finite differences. That's why we use the analytical Jacobian, because it's much faster to compute. So the step length, let's focus on this step length QK, is determined by solving this linear least squares problem here, which comes from this linearization. So we first stack the real and the imaginary part of the residual function, and we do the same with the Jacobian matrix of the residual. We solve this linear least squares problem, and we lead to this iterative scheme. So the electrical conductivity sigma k plus 1, so the iteration k plus 1 is equal to sigma k plus this step length, which is obtained from this linear least squares problem, which is equal to this quantity here, where J tilde K daga is the Morpenrose pseudo-inverse matrix. So now we have two difficulties here. The first one is that the Gauss-Newton method is convergent, but in applications may be not convergent. So in order to ensure the convergence of our numerical algorithm of this iterative method, we introduce a parameter alpha k, which is called damped parameter and is chosen by Darmigio-Goldstein principle. So basically, we are looking for this parameter alpha k of the form 1 over 2 to the power I, which verifies this inequality here. Moreover, this choice of alpha ensures the convergence of the iterative method, but we also want the positivity of the solution, because from the geophysical point of view, the fact of getting a negative values for sigma has no sense. The electrical conductivity is also positive. So we choose the parameter alpha, which verifies this inequality here in order to ensure the convergence of the method. And we also control the positivity of the solution. So once we have solved this difficulty here, the difficulty of the convergence of the method, we also have another difficulty. The another difficulty is that this matrix here, JK tilde, is very ill-conditioned. So we cannot find the step length Q in this way anymore. We need to regularize the problem. So we regularize first in a smooth way. So we introduce a regularization matrix L, which can be the identity matrix, the first derivative operator, or the second derivative operator. This is the main choices. We consider the generalized singular value decomposition of the matrix per J tilde K and L. So we decompose the two matrices in this way, where U and V are orthonormal matrices, Z is non-singular, is a non-singular matrix, and sigma and M are diagonal matrices, which contains the singular values of J and L respectively. And we get this TGSVD solution QK, which is the step length in our iterative scheme. So the only thing that remains here is how to choose the regularization parameter, because in this kind of regularization, the main idea is to approximate the Jacobian matrix by a low rank matrix. So the regularization parameter tell us where to cut in some way our matrix in order to get a good approximation of the matrix with a smaller rank. So basically we work with a limited number of singular values of J. So the three ways for choosing, for finding this regularization parameter are these three methods. The first one is the discrepancy principle, and is very accurate, but only in the situations in which we know the distribution of the error in the data. So we need to know the perturbation in the data. We used it in the cases in which we work with the synthetic data, for example, because we introduce the perturbation in the data, so we know the distribution of the noise and we can apply the discrepancy principle. But in the situations, for example, in which we don't know what is which is the noise in the data, we use the L-curve method, which was introduced by Hansen in 1988. And basically this method chooses the regularization parameter as the corner of this curve here. So is the value of L which minimizes at the same time this quantity and this quantity. In general situations, this curve has an L shape. That's why the method is called L-curve method. And the regularization parameter is the corner of this L shape. Another choice for the regularization parameter is the optimal choice. And it corresponds to the regularization parameter which provides the smallest error between the measured data and the exact data. So after this smooth regularization, we asked ourselves why, if we know we have a prior knowledge about the exact solution or the distribution of the conductivity, and maybe it's not smooth, maybe it's a piecewise constant function, or it could be non-smooth. A non-smooth function, non-smooth distribution. So we introduced this sharp regularization, which is a non-smooth regularization based on the minimum gradient support. And it was introduced in this work here in 1989. So basically, if we substitute the norm of LQ here by this regularizer, which depends on the regularization matrix L and also on these two parameters, tau and epsilon. In our experiments, we will fix epsilon to 1, and we will vary tau. And basically, it works as the smooth regularization if the difference between two consecutive iterations of the method, of the algorithm, is very small. So when the difference between sigma k plus 1 and sigma k is very, very small, the regularizer SQ understands that the distribution of the exact solution is smooth. However, if the difference between two consecutive iterations is large, it understands that the distribution of the exact solution could be non-smooth. So it acts as a sharp regularizer or a non-smooth regularizer. Here we introduce the concept of the depth of investigation. which represent usually refers to the depth below which data collected at the surface are not sensitive to the physical properties of the surface. In short, the DOI, the depth of investigation, provides an estimation of the maximum depth that can be investigated from the surface, given a specific device and the physical properties of the soil. So basically, we after some mathematical steps, so we introduce a perturbation data, a perturbation delta in the data. We do some mathematical steps, and we get the definition of the sensitivity of the data as in this form here. So this sigma r represents the sensitivity of the data at depth set r. So represent the relative sensitivity, yes, of the data vector to a perturbation in the conductivity of the ground layer set r. And when this sigma r decreases significantly with respect to sigma 1, so the sensitivity at the surface, the recorded conductivity for the earth layer is not strictly related to the data or to physical properties of the subsoil. So basically, this sigma r tells us the depth till which we can be sure that the reconstruction is trustable. And now I will show you some numerical experiments. In this first numerical experiment, we report on the top row the reconstruction of the electrical conductivity on synthetic data for a data corresponding to a CMD Explorer, which is a device which works with 3 intercoil distances and 1 frequency. We choose the matrix regularization as the second derivative operator. We worked with a smooth test profile sigma, and we introduced a Gaussian noise in the data of level 10 to minus 3. So on the top row, we inverted the complex signal and the quadrature component of the signal for both the orientations of the device. And on the bottom row, we inverted the complex signal and the quadrature component of the signal just for the vertical orientation. So we can see that in both cases, the reconstruction of the complex signal is more accurate than the quadrature than the inversion of the quadrature component, which is what we wanted to show in this work, because as I was saying at the beginning of the presentation, the fact of neglect part of the data means that you are losing information in some way. So maybe some situations is sufficient to invert just the quadrature component. I mean, the reconstruction is still good because it is able to find the shape of the exact solution. But anyway, you are losing information, and sometimes it is also good to use all the data. And this is the proof. I mean, the reconstruction of the complex signal is better than the inversion of the quadrature component. And the same happens for the vertical orientation. Here we increase the noise in the data. So the level of the noise is 0.2. And obviously the reconstructions are worse. But anyway, the inversion of the complex signal in some way is able to follow the shape in some way of the exact solution. So it is able to to find at which depth the maximum is, and more or less the value of the conductivity at that depth. Obviously, the reconstruction is worse than before because the noise in the data is bigger, but still the reconstruction of the complex signal is much better than the reconstruction of the quadrature component of the signal.
Patricia, sorry.
Yeah.
Can you have a couple of minutes at most?
Yeah.
Okay, thank you.
Okay. Okay. So here we changed the test profile. So we choose a stepwise constant, piecewise constant function. In the top row, we regularized in a smooth way. And on the bottom row, we regularize with the MGS regularizer. And we can see that the smooth reconstructions are good in the sense that they are able to find the shape in some way of the exact solution, but the non-smooth regularizer gives us a more complete reconstruction, and it is able to find the shape of this piecewise constant function. So here we have a two-dimensional true model, which we want to find. We have the three smooth reconstructions for the different regularization matrices, and here we have the non-smooth reconstruction for different values of tau. So we can see that the reconstruction with the smooth regularizer are good, but it is not able to reconstruct in a very good way the transition between the high values of the conductivity and the low values of the conductivity. I mean, it works like a smooth, it changes in a smooth way, which is what we expect because it's a smooth
Non l'hai messo te? Oh, perché metti poca acqua?
Sorry?
Yeah, no, don't worry about it. It was
okay.
some spurious noise.
Okay. Okay, and we have here on the right the non-smooth regularizer. You can say obviously that the reconstruction with the non-smooth regularizer are not so good as the smooth reconstruction, but from the point of view of the change, the high change between the values of the conductivity, it is able in a better way to reconstruct this transition here. So the change between high values of the conductivity and low values of the conductivity. Here we took the third column of the two-dimensional synthetic model just to see how the algorithm was working with the different regularizations. So in the first graph we have the smooth regularization with the first derivative operator, and this tree graph corresponds to the three different MGS regularizations for three different values of tau. And we can see that the reconstruction with the MGS is better than the smooth one. And here we have the inversion of experimental data, which was recorded at Parco Naturale di Molentargius in Cagliari. So here, this is Poeto Beach. I don't know if you know, it's the most famous beach in Cagliari. and the geophysicist that works with us, Giampiero from the University of Cagliari, collected the data along this red line, go and back, and we inverted this the data, the collected data here. So, okay, these are some information about the recorded data, so the apparent conductivity of the soil. And this graph displays on the top row the quadrature component of the data, so the imaginary part of the collected data, and on the bottom row the real part of the collected data for both the orientations and for the three distances of the coils between the coils, because we collected the data with the CDM Explorer, which works with 3 intercoil distances and 1 frequency. So basically, these are the data that we inverted in order to get the distribution of the electrical conductivity, and these are the 2-dimensional reconstructions. So the first graph corresponds to the first derivative operator as the regularization parameter. The second one is the second derivative operator as the regularization parameter, and the third one corresponds to the MGS regularizer, so non-smooth regularization. We confirm that the best reconstruction is the second one, which was decided also by the geophysicist who works with us, and it is very, very good reconstructions, because we expected to find like a wall of soil water from 1 meter of depth, if I remember well. So we can see here that close to the surface, the conductivity is very, very low, so there's no conductive substance. And then from 1 meter of depth, we can see that the value of the electrical conductivity increases, which is what we expected to have. In this case, for example, the non-smooth regularizer wasn't work as well as the smooth one, but still it is able to reconstruct in a good way the transition between the low values of the conductivity and the high values of the conductivity. I forgot to tell that these 2-dimensional reconstructions was obtained by inverting, in this case, 200 one-dimensional inversions, so one independent of the others. So there's no lateral constraint, there's no regularization, horizontal regularization, and that's why here there are some points in which there is like non-horizontal sense. I mean, there is some problems here, because the inversions were computed independently one from the others. The black line represents the depth of investigation, so the depth till which we can be sure that the reconstruction is trustable. And all the computed examples were run through this graphical interface made in MATLAB with Giampiero Deida, Caterina Fenu, Giuseppe Rodriguez from the University of Cagliari, and Gabriele Lovicu, who was our student. And you can download this graphical interface, and you can play by changing all the parameters, the possible parameters. You can see the different results depending on the choices that you take also for the regularization, or maybe you can inverse just the quadrature component or the in-phase component, or maybe the complex signal. You can you can generate the data, synthetic data, and then invert it in order to see if the algorithm works well, or you can play and have fun. So the works in progress are to do the MATLAB graphical user interface for the forward model, because it's useful for the geophysicist in order to understand maybe which kind of device or which kind of data is convenient depending on the area that they want to study. The two-dimensional reconstruction with lateral constraint in order to get an horizontal regularization and remove these problems here, and we are working on it together with Alessandro Buccini. So if you have suggestions, we are happy to hear you. We also are working on the resolution of the nonlinear model by the numerical treatment of the Henkel transform involved in the integral equations, because the integral equations of the model can be expressed also as a Henkel transform. So we are studying another algorithm to solve the nonlinear model and compare it with to our numerical algorithm. So as future work, we will reconstruct the soil geometry from other kinds of data, like seismic data, maybe adapting our algorithm, or maybe starting from a new one. And we also want to invert the electromagnetic data in time domain. And this is all. And thank you for your remote attention.
Thank you, Patricia, for the very, very nice talk. So is there any question? You can either unmute yourself or write them into the chat, which I have opened. I'm giving just a couple of seconds, because if they're typing, it might take a while. So in the meantime, I actually have one thing, a curiosity. So the linear and nonlinear model. So basically, you said like the linear model, sorry, works only for very tiny values of the sigma.
Yes, this one.
Yeah.
Yes,
so
it was introduced for a specific device.
So it's basically like a Taylor expansion of the nonlinear one, something like that, around the origin.
Sorry?
So it's some sort of, let's say, Taylor expansion of the nonlinear model around the origin. So some sort of a linear approximation.
Yeah.
Could it be used instead of the Jacobian in the Gauss-Newton method?
Could be.
Because used instead of the Jacobian, because maybe, I mean, this looks like a convolution. Well, besides there is a plus and not a minus, but so maybe this, I mean, this discretization of this thing will have a structure, even if it's just a locally Toeplitz one.
But you are saying about the linear model?
Yeah, using the linear model in the Gauss-Newton one as instead of the Jacobian matrix.
Yeah, no, the Jacobian matrix has the not the coefficient matrix that you get by discretizing this model structure.
Okay.
I don't know if I answered your question.
Yeah, no, you did.
Okay.
Is there any other question from the participants?
Or maybe suggestion for us?
Yeah, maybe I have one.
Yeah.
Thank you for your great talk, Patricia. How do you, can you repeat please, how do you select your regularization parameter? And I just curious how you choose it also in practical application, well, in real application.
Here, okay. For experimental data, we use the L-curve method.
Okay.
Basically, we choose the regularization parameter as the corner of this this curve here, because also the discrepancy principle is accurate, but you can use it just when you know the distribution of the noise in the data. So obviously, when you are working with experimental data, you don't know the noise. So we used this this method here, which in general should have an L shape, but sometimes this L shape is a little bit disturbed.
Yeah, and according to you, does it work as better as
this method?
yeah, the L
Yeah, it's work. Yeah.
Okay, thank you.
Yeah.
And if there is time, I want also to ask you about the prior that you have fixed. If you have a prior here on your
no, we don't have it. No.
But you don't have it because in some sense, how can I say, there is no need to fix a prior because you just need your inversion term, or I don't know why.
We don't need it. I mean, we don't need to have a prior in this algorithm. It's not necessary. So.
Oh, okay.
Anyway, we haven't tried. I mean, like the algorithm works in this way, but maybe if we introduce a prior, maybe the reconstruction gets better. I mean, it is possible, but we didn't use it.
Okay. Thank you.
You're welcome.
Other questions, doubts, suggestions? That would actually be very helpful. Okay. No one has any other question, I guess we can thank Patricia for the excellent talk.
Thank you for your attention.
And we will see, I guess, in another 2 weeks. Before that,